Hello, and welcome to section 6.5 on exponential growth and decay. In this section, we will consider some basic applications of the natural exponential function. The examples that we will consider are population growth, radioactive decay, and Newton's law of cooling. We will only consider functions f with the property that the rate of change of f is proportional to f. More precisely, functions f with the property that f prime of t is equal to k times f of t, where k is a constant. Setting y equal to f of t, we can rewrite this as dy dt is equal to k times y. This is called a first-order differential equation. It turns out that functions y satisfying this equation have a particular unique form, namely y is equal to c times e to the kt, where c and k are constants. Note that if y equals c e to the kt, then dy dt is equal to c times k times e to the kt, which is k times ce to the kt, which equals k times y. So y indeed satisfies the differential equation. Observe that if t equals 0, then y of 0 is equal to c times e to the k times 0, which is just c. This is called the initial value. Thus we can rewrite the equation y equal to c e to the kt as y of t is equal to y of 0 times e to the kt. If k is less than 0, then this equation is called the law of natural decay. And if k is greater than 0, then this equation is called the law of natural growth. Solving for k in the equation dy dt equal to ky, we have that k is equal to 1 over y times dy dt. The constant k is called the relative growth or decay rate. In practice, it is thought of as a unitless ratio, and it can be expressed as a percentage by multiplying it by 100. We will now discuss some plausible scenarios where the rate of change of y relative to y is fixed. Our first application is population growth. We write our equation as p of t is equal to p sub 0 times e to the kt, where p of t is the population after t years, and p sub 0 is the initial population at time t equal to 0. Example 1. The world population was 2,560 million in 1950 and 3,040 million in 1960. Find the relative growth rate. Note that our initial population is p sub 0 equal to 2,560. So p of t equal to p sub 0 e to the kt is equal to 2,560 e to the kt. 10 years later, we are given that the population is 3,040 million. Writing this in equation form, we get p of 10 is equal to 2,560 times e to the 10k, which is equal to 3,040. To find the relative growth rate k, we must solve the equation for k. To do this, we rewrite the equation as e to the 10k is equal to 3,040 divided by 2,560. And we apply the natural logarithm to both sides. We obtain 10k is equal to the natural log of 3,040 divided by 2,560. So k is equal to the natural log of 3,040 divided by 2,560, all divided by 10, which is approximately 0.017185. Thus, the relative growth rate is approximately 1.7% per year. Our next application is radioactive decay. We write our equation as m of t is equal to m sub 0 e to the kt, where m of t is the remaining mass at time t, and m sub 0 is the initial mass at time t equal to 0. In practice, radioactive substances have been found to decay at a rate proportional to the remaining mass, so k is less than 0. The rate of change, dm dt, is the rate of decay. Scientists express the rate of decay in terms of half-life, which is the time required for half of any given quantity to decay. Example 2. The half-life of radium-226 is 1,590 years. A sample has a mass of 1,000 milligrams. Find an equation that expresses the mass at any given time t. We are given that the initial mass, m sub 0, is equal to 1,000. So our equation becomes m of t is equal to 1,000 e to the kt. All that remains is to find k. We are given that the half-life is 1,590 years. So in 1,590 years, the mass of our sample will be reduced by half. Expressing this mathematically, we get m of 1,590 is equal to 1,000 e to the 1,590 times k, which is equal to 1/2 times 1,000. Canceling, we are left with e to the 1,590k is equal to 1/2. And applying the natural logarithm to both sides, we have that 1,590k is equal to the natural log of 1/2, which is the natural log of 1 minus the natural log of 2, which is just negative the natural log of 2. Therefore, k is equal to negative the natural log of 2 divided by 1,590. And our original equation becomes m of t is equal to 1,000 e to the negative natural log of 2 divided by 1,590 times t. For radioactive decay problems, if you obtain a positive value of k, then you have made a mistake. Now part B, when will the mass be reduced to 30 milligrams? To answer this question, we need to solve the following equation for t. m of t equal to 1,000 e to the negative natural log of 2 divided by 1,590 times t is equal to 30. We rewrite this as e to the negative natural log of 2 divided by 1,590 times t is equal to 30 divided by 1,000, which equals 0.03. Applying the natural logarithm to both sides, we obtain negative the natural log of 2 divided by 1,590 times t is equal to the natural log of 0.03. Solving for t, we get that t is equal to negative 1,590 the natural log of 0.03 divided by the natural log of 2, which is approximately 8,044 years. We conclude with the trickiest application, Newton's law of cooling. This law states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. Let capital T of t denote the temperature of the object at time t, and capital T sub s denote the temperature of the surroundings. We can formulate Newton's law of cooling in terms of a differential equation. dt dt is equal to k times capital T of t minus capital T sub s. Note that dt dt is d dt of capital T of t minus capital T sub s. So while the above equation looks different, it still has the form dy dt is equal to k times y. Here, y is equal to capital T of t minus capital T sub s. Thus, the solutions to the above differential equation have the form capital T of t minus capital T sub s is equal to capital T of 0 minus capital T sub s times e to the kt. Example 3. A bottle of soda at 72 degrees Fahrenheit is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the bottle is cooled to 61 degrees Fahrenheit. What is the temperature of the bottle after another half hour? We are given that capital T sub s is equal to 44. So the solution to Newton's law of cooling is capital T of t minus 44 is equal to capital T of 0 minus 44 times e to the kt. Once we find k, we can solve the problem. First note we are given an initial temperature of 72 degrees Fahrenheit. So capital T of 0 is equal to 72. Thus capital T of 0 minus 44 equals 28. Hence, our equation becomes capital T of t minus 44 is equal to 28 times e to the kt. We are also given that after half an hour, the bottle has cooled to 61 degrees Fahrenheit. Thus T of 30 is equal to 61, and T of 30 minus 44 is equal to 17. In putting this into our equation for t equal to 30, we get 17 is equal to 28 times e to the k times 30. Thus, e to the k times 30 is equal to 17 divided by 28, and applying the natural logarithm to both sides, we obtain that k is equal to the natural log of 17 divided by 28 divided by 30. Therefore, our original equation is capital T of t minus 44 equals 28 times e to the natural log of 17 divided by 28 divided by 30 times t. Or, capital T of t is equal to 44 plus 28e to the natural log of 17 divided by 28 divided by 30 times t. We are now ready to determine the temperature of the bottle after another half hour. This will amount to plugging in T equal to 60 into our equation. T of 60 is equal to 44 plus 28e to the natural log of 17 divided by 28 divided by 30 times 60, which is approximately 54.3 degrees. So after another half hour, the bottle of soda will cool to approximately 54.3 degrees Fahrenheit.